Hello everyone. So today our discussion will be on development leading to Bohr's model. So today we will discuss some developments, okay, or some discoveries which leads to the Bohr models, okay. So before going to the Bohr model, we are going to discuss some discoveries. Please go through page number 33 in your textbook, okay, about the discovery of X-ray and then radioactivity, okay. Please read it through, okay, at your home. X-ray and radioactivity. So the discovery of X-ray and then radioactivity, and then further discovery and development, okay, such as the dual character of electromagnetic radiation, okay. So dual character, as you have studied in your class 10 standard, okay. By dual character it means it possesses both wave and particle nature, okay. So light or electromagnetic radiations possess both wave like and particle like nature. So we are going to discuss this also. And then atomic spectra. So every element exhibit its own spectra or color, okay, in the spectrum, electromagnetic spectrum, okay. So these two development, okay, these two development or these two discovery leads to the Bohr model of, okay, Bohr model. So let's discuss the first topic, wave nature of electromagnetic radiations. So first we are going to discuss the wave and then slowly the particle nature. The wave nature of electromagnetic radiations, okay. So this nature of electromagnetic radiations, okay, was given by James Maxwell in 1870, okay. So he found out that electrically charged, okay, particles move under acceleration, okay. So when an electrically charged particles move under acceleration, alternating electrical and magnetic fields are produced. So when electrically charged particles, okay, moves under accelerations, alternating electrical and magnetic fields are produced, okay. Example, electron, okay. When electron moves, okay, they gives electrical and magnetic fields, okay. So these fields, okay, these fields electrical, as from the name also we know, electric and magnetic, okay. So electrical and magnetic fields, okay, they are transmitted in the form of waves, okay, transmitted in the form of wave, and we call this wave as electromagnetic waves or electromagnetic radiation. So this transmitted electric and magnetic, okay, they are transmitted in the form of waves, and we call it as electromagnetic waves or electromagnetic radiation. So Newton also suggests that light has particle nature, or he called it as corpuscle, okay. So corpuscle means particle, okay. And later on in the 19th century it was found that light also have, or electromagnetic radiations also have wave nature. So to understand better, let us see a diagram. This, let us suppose this as y-axis, z-axis and x-axis in order to show the three-dimensional, okay, diagram. So let us suppose this is magnetic field, okay. So they are moving in wave, okay, or they propagate in wave. Magnetic field component, okay, magnetic field component. He observed that they moves in wave, okay. Let us suppose this move along y-axis, and the electric field, okay, perpendicular to y-axis, okay. Let us assume it move from z, okay, z-axis. So we found out that this electric field and magnetic field, okay, they are perpendicular to each other. So Maxwell was the first to reveal that light waves are associated with oscillating electric and magnetic character. So this oscillating electric and magnetic field, okay, produced by oscillating charged particles, okay, are perpendicular to each other, and both are perpendicular to the direction of propagation, okay. So these are electric and magnetic, they are perpendicular to each other, and then these two are perpendicular to the direction of propagations, okay. So I've written this in short form, okay, perpendicular. So these electromagnetic waves do not require medium, okay, and they can move in vacuum. Example, sunlight, okay, can reach our earth, okay. It does not require any medium to pass through the atmosphere to reach the earth, okay, unlike sound waves or waves, okay, in water. So there are many types of electromagnetic radiations, okay. There are many types of electromagnetic radiations which differ from one another in wavelength, okay. There are many types of electromagnetic radiation, they differ in wavelength or frequency, and the arrangement of electromagnetic radiation in order of the increasing wavelength and decreasing frequency, okay. The complete spectrum obtained is called electromagnetic spectrum. So sun, okay, sun emit electromagnetic radiations, okay. So the electromagnetic radiations, okay, has different wavelength and different frequency, okay, but only the visible region, okay, only the visible region is visible to the human eye, okay. The rest are invisible, okay, to our naked eyes. So there are different wave and different frequency and different wavelength, okay. And then visible region, okay, is from 400 nanometer to 750 nanometer. This is the visible region, okay. That is why we are able to see, okay, the visible light to our naked eyes. Different kinds of units are used to represent electromagnetic radiations, okay. So usually wavelength and frequency, okay, are used, okay, to represent the units, okay, of electromagnetic radiations. The first one, wavelength, represented by lambda, okay. This wavelength is the distance between two consecutive rays or graph rays, okay, and graph. So in the wavelength, okay, we see the rays and the graph, okay. The distance between two rays is the wavelength, or between two graph is the wavelength. So this wavelength is expressed in Armstrong, nanometer, picometer, or meter. So please know this value, okay. 1 Armstrong is equal to 10 to the power minus 8 centimeter, and when converted to meter it is 10 to the power 10 minus 10 meter. And then 1 nanometer, when converted to meter it is 10 to the power minus 9 meter. 1 picometer, 10 to the power minus 12 meter, okay. So these values, remember, and this will be helpful for your numerical problems. The next unit, okay, frequency, represented by nu, okay. It's somehow look like V. It is the number of waves passing through a point in 1 second, okay. So one cycle, okay, in 1 second. So this is the unit is expressed in hertz, okay, or cycle per second, or second per second, okay. So 1 hertz is equal to 1 cycle or second. Next is wave number, okay, represented by a bar above the frequency. It is the number of waves present in 1 centimeter. So the number of waves present in 1 centimeter, it is the reciprocal of wavelength. So this is expressed in meter per meter or per centimeter. So usually it is expressed in centimeter inverse. Now velocity, okay, velocity is the distance, okay, traveled by wave in 1 second, represented by c, okay. So this c denotes the speed of light. The value of light is speed of light is 3 into 10 to the power 8 meter per second. So c is equal to wavelength into lambda. Okay, so from this relation we can derive another relationship. So we can say lambda. Lambda is equal to c by frequency is equal to c by lambda. This means that as frequency increases, lambda decreases or wavelength decreases. Suppose the frequency increases, then the length this length it will decrease, or wavelength will decrease, and then lambda or frequency, if this frequency increases, wavelength increases. If this wavelength increases, frequency decreases. Suppose the wavelength increases, then frequency will decrease. This can be seen through the diagram also. Frequency increases in this direction, in the electromagnetic spectrum. Frequency increases in this direction, and then wavelength increases in this direction. They are opposite. So through this value, remember these values, and this will be helpful for your numerical problem. Let's do one problem. A yellow light is emitted from a sodium lamp and has a wavelength of 580 nanometer. Calculate the frequency and wave number of the yellow light. Yellow light means it is in the visible region. That means 500 nanometer falls in the visible region. So what is given is wavelength. 580 nanometer. So frequency is given by nu. So nu is equal to c by wavelength or lambda. So 1 nanometer is equal to will be equal to 580 into, when we convert to meter, it will be 580 to 10 to the power minus 9. So we'll calculate this one. C, as we know, the value is 3 into 10 to the power 8 meter per second, and lambda wavelength given 580 to 10 to the power minus 9 meter. So we can cancel this meter and we get 5.17 10 to the power 14 per second. Next is wave number. So wave number is given, formula is 1 by lambda, reciprocal of wavelength. Lambda, we know the value is 580 into, as we have discussed earlier, usually wave number is given in centimeter inverse. So we'll convert this to centimeter. 7. So now we will find this value, 1 by lambda 1 by 580 into, so we'll get Part-4 inverse. So this is one numerical problem. So in your textbook, please try from your textbook, please practice exercise or problem 2.3, 2.4, 2.5, page number 39. Okay. Practice these questions, okay, for better understanding. So wave nature of electromagnetic theory, okay, could explain diffraction and okay, so this wave nature, okay, could explain the phenomenon of diffraction and interferences, okay, in nature. So about these fractions you have studied in your class 10 also. So when light pass through, okay, from one medium to another medium, diffraction takes place, okay. Suppose this is water, okay, a beaker and water, and you keep a pen, okay, so it look like it's bending, okay. When light pass through this water, this pen look like bending, okay, with our naked eyes, okay. So this is as a result of diffraction, okay. This shows that electromagnetic waves, okay, radiation are wave-like. Interference, okay. When we take the example of waves, okay, and there is another waves, okay, so this trough or crest, okay, they overlap, okay, with the trough of the another wave, okay. So this will cause, or this will result in another wave, okay, with smaller amplitude, okay, resulting in destructive interference, okay. So since both are opposite, okay, and then they affect, okay, the force, and then this result in smaller wavelength, okay, smaller wave, and we call it as destructive interference. Let us take another example. Another wave, and then another wave comes and meet, okay, and they, let us suppose they overlap, okay. So since they overlap, it will give rise to a wave of higher amplitude, and we call it as constructive interference. However, this wave nature of electromagnetic theory could not explain the nature of radiation from hot bodies, okay, black body radiations, ejection of electrons from metal surface when radiation strikes it. We call it as photoelectric effect. Variation of heat capacity of solid as a function of temperature. Line spectra of atoms with special reference to hydrogen. These things we will discuss later. Why this wave theory could not explain this nature of radiation in whole bodies, ejection of photoelectric effect, or variation of heat capacity of solids as a function of temperature, line spectra of atoms with special reference to hydrogen.